Hey everyone, Mr. Fransky here. Hope you're having a great day. Today we're going to talk about 6.6a, which is the first part of DeMoivre. DeMoivre, French name, and came up with some pretty cool stuff regarding complex numbers. So we're looking a little bit at complex numbers today. Remember, that's the letter I, which is the square root of -1. And it's kind of weird that this comes after the parametric and polar graphing, but it actually has a lot to do with vector sums and also with graphing and polar. So it's kind of a cool little way to end chapter 6. So let's take a look. So first for bell work, if you just want to pause the video, you can try this on your own, but v is 2, -1, w is 1, 3. I want you to plot v, w, and v plus w in standard position. If you want to give that a shot, we'll come back and try it in a sec. All right, so v is 2, -1. 1, 2, -1, that's right there. So that vector would look like that. Remember, it has a direction. W is 1, 3, so it's going to look something like this. And then the sum, v plus w, it's add components, so it's going to be 2 plus 1, which is 3, and then -1 and 3, which is 2. So that would look something like this, right there. Okay. Remember, we have that property where if we were to put these in standard position, so the first one, let's put v in red. So v 2, -1, something like that. And then maybe we'll use yellow to show if we add w to that, it's going to end up getting right to the place where v plus w is. So vector addition, not that hard. We've seen it back at the beginning of chapter 6. And so now just bring it back here because it's going to relate to what we're going to do today. So the complex plane. The complex plane looks a lot like the xy coordinate plane, but instead of x and y, we label it r and I. Okay, so the x-axis is what we call the real line, and the vertical axis, the y-axis, is what we call the imaginary line. So you can plot any number, any complex number in the complex plane, so like, for example, 2 plus I. 2 plus I is 2 on the real line, because that's the real part, right? A plus bi, if we think about it. And then we go up to 1I, so it'd be right there. This right here would represent 2 plus I. Okay, so some other stuff, we could do like, I don't know, -4 plus 5I. Think about where that would be plotted. When we go to -4 on the real axis, and then we go to 1, 2, 3, 4, we're going to run out of space, 5I. So it'd be like right up here. Okay, -4 plus 5I. Now you can graph real numbers too. So like if you wanted to graph just like 6, that'd be 1, 2, 3, 4, 5, 6, and there would be no I component, right? So that right there would just be 6. You do the same thing if you're like -2I. -2I would just be right here. That'd be -2I. Purely imaginary number, it's called. But basically, we just open up this way of graphing complex numbers. Okay, so we have the real line and the imaginary line. And we can plot any complex number using those two. So let's go back to our bell work and write it a little bit differently. So if our first complex number, often use z, which is a plus bi, and that would always plotted at the point a comma b, because it would be a on the real line and bi, so b on the imaginary line. Excuse me. So z is often used for complex numbers. So if z is 2 minus I and z1 is 2 minus I, z2 is 1 plus 3i, I want to plot z1, z2, and z1 plus z2. So let's think about what that would look like. Well, z1 we plotted at 2, -1. That's right there. Okay, so that's z1. Let's label z1. Z2 would be at 1 plus 3i, so that's 1, 1, 2, 3 right there. That's 1 plus 3i, that's z2. And then z1 plus z2. So when you add complex numbers, you add the real parts, which is going to be 3. And then you add the imaginary parts, which is plus 2i. So we graph 1, 2, 3 plus 2i. You'll notice the work we had to do for this, that's equal to z1 plus z2, was exactly what we had to do for the bell work. If we go back to the bell work problem, there we go, we see that we had 2, -1, 1, 3, and then when we added them together, we added the x components and the y components, which is equivalent to adding the imaginary and real components of the problem we just did. So vectors, very, very similar to how we're dealing here with complex numbers. Okay, so when we think about graphing vectors in the plane, graphing complex numbers in the plane is pretty much doing the same thing. Cool. So we need to define what we call the absolute value of a complex number. So if I have z is a plus bi, then the absolute value or modulus of a complex number. So you can denote that with absolute values. So absolute z, which is the same thing as absolute a plus bi. Okay, and the way you evaluate it, you might know this already with vectors, right? If you think about the absolute value of a vector, it is the square root of a squared plus b squared. Okay, so that is a definition. And if you think about it in the plane, so let's say we're at like 1, 3 from bell work, what does that give us? What does square root of a squared plus b squared give us? This is a, this is b. That gives us the length. Okay, so the length of the vector, or the length of, kind of weird to think about the length of a complex number, but that is the absolute value of z, which is the square root of a squared plus b squared. Okay, so it just gives us the length like we've been doing before. It's just Pythagorean theorem to give us the length of a complex number, the distance from 0, 0 to a plus bi. So, I guess I didn't have an example. Let's have you try a couple of these. So let's find the modulus of z1. Let's do, I don't know, 3 minus 4i. z2, let's do 1 minus 2i. And z3, let's do negative 6 plus i, something like that. So find modulus z1, modulus z2, modulus z3. Okay, so why don't you give that a shot. All right, hopefully you're able to find these, not too much difficulty. So modulus of z1 would be square root of 9 plus 16, right? We're just a squared plus b squared, so that's square root of 25, which is 5. z2 would be square root of 1 plus 4, so that'd be root 5. And z3, square root of 36 plus 1, which is square root of 37. Okay, so not too tough to find the distance of a complex number away from the origin, or the modulus or absolute value. All right, so trigonometric form of a complex number. So right now we have this way of talking about like this is like a plus bi. Okay, it gives us an a component and a b component. So how do you think it would work if it's like polar? Well, we need the length, which we know is square root of a squared plus b squared. It's the modulus. And then we'd have to find the theta, right? And to find theta, we can make a triangle. This would be a b distance, this would be a, and we could somehow use tangent or something. So trigonometric form of a complex number. So we know z can be written a plus bi. So to write it as a complex number, if we just think about a and b, a would be the modulus cosine theta, so absolute z cosine theta, right? This is just like polar, or vectors for that matter. And b would be modulus z sine theta, okay? And that would be true anywhere that you are, okay? As long as you think about theta measured from standard position. So that means that z can be written a plus bi, so that's modulus z, let's see, modulus z cosine theta, that's our a, plus modulus z sine theta, and then we have to have an I at the end. So convention for this is instead of writing absolute z every time, we write r. So we say let absolute z equal r, and now we can pull that out. So z would be equal to r times cosine theta plus, I'm going to bring the I to the front, I sine theta. The reason I bring the I to the front is because writing sine theta I, the question is like, well, are you taking the sine of theta I, or are you doing sine of theta and then multiplying by I? And that's the second one is what you want. You want to do the sine of theta, then multiply by I. So this is just a new way of writing z equals a plus bi. Okay, so these are the same thing. Same exact thing. You can write it in, this is called trig form. It looks a lot like polar. Or you can write it in, this is called standard form. Okay, so trig form has the cosine and the sine. Really all we're doing is we're saying we know the angle, we're extending it out the distance r. Yeah. So what we want to do here is find trigonometric form of each complex number, and we'll find it using theta between 0 and 2 pi. We'll do these together. So what we're doing here is we know a plus bi, and we want to find what is theta and what is the r distance there. So first one we're doing with no calc. Hopefully it'll be a nice value we know. So we got 1 minus 3i, so that'd be positive 1 right here, and then minus root 3, excuse me. So let's say this is root 3, this is positive 1. So there is our point right there. So that point right there is at 1 minus root 3i. And now we're going to try to translate this into trig form. So we're going to think about how far our angle is around this way. And they tell us to use between 0 and 2 pi, so we're going to be using radians. So first let's do our r. So r in this case, which is the modulus of z, square root of a squared plus b squared, that's 1 plus 3. Hey, that's a nice number. Square root of 4 is 2. So we know our r. And now we're going to try to find theta. So if I make a little triangle here, I like to make it against the x-axis. So this is a value of root 3. This is a value of 1 right in here. So if we're trying to find, let's say theta is right there. I'll put my 1 up there. So tan theta would be equal to root 3 over 1, opposite over adjacent, so that's root 3. Hey, I know that. Tan theta is root 3 at 60 degrees. So if we're short of 360 by 60 degrees, that means theta. I should have used a different letter for this. Let's change that letter. I don't want to be confused there. To get rid of that theta, let's change that to an x maybe, huh? So we put a little x right there. This is x. So I know x is 60 degrees. So then theta, which is all the way around from in positive standard position, theta would be 60 degrees short of 360, so it would be 300 degrees. Okay, so now we just write this in trig form. So it would be 2, because that's our r. So z is equal, this is just a different way of writing it. 2 times cosine 300 plus I sine 300. And you can try it, right? Cosine of 300 is positive 1/2. 1/2 times 2 is 1, so that checks out. And then sine of 300 is negative root 3 over 2. 2 times negative root 3 over 2 is negative root 3i, so it works out. Okay, so that's what I'm looking for when I ask for trig form. It'll seem weird because I want to take cosine of 300, but you just leave it, right? Cosine theta plus I sine theta. Next one we're going to need a calculator for, so let's see what's going on. We got negative 3 minus 4i. 1, 2, 3. 1, 2, 3, 4. There's negative 3 minus 4i. Need to find this theta right here. So let's make another x. Put it right in this corner against the x-axis. So tan x, we know this distance right here is 4, this distance is 3. So tan x is equal to opposite over adjacent, that's 4/3. Okay, so x is going to be tan inverse of that. This is going to be your calculator. I'll grab mine. We're going to do second tangent of 4/3. And we're asked for a value between 0 and 2 pi again, so I'm going to make sure I'm in radian mode. I get 0.927 radians. And that is 0.927 radians beyond pi. So theta is going to be that guy. Let's write it out. 0.927 plus pi. So let's add pi to that. And that gives me 4.06 radians. So we got theta. Now let's figure out r. So r is going to be the square root of 3 squared plus 4 squared. That's 9 plus 16, which is 25. So r is 5. So z, another way of writing it in trig form, is going to be 5 times cosine of 4.06 plus I sine 4.06. And if you grab your calculator in radian mode and you type these in and multiply by 5, you will get negative 3 and negative 4. So it's just a different way of writing these complex numbers in what's called trigonometric form. And you're going to see why this is so useful next. So, multiplication and division of complex numbers in trig form. So we couldn't multiply vectors, right? When we had like v equals 2, 1, and w equals like 4, negative 7, something like that, we couldn't multiply them. We talked about the dot product and just touched on the cross product, but dot product like gave us a number. It did give us a new vector. Complex numbers, remember, like if you have like 2 plus 3i, you want to multiply by 3 minus 4i, something like that. You can multiply these, and they will give you a new complex number, right? You would have to FOIL, right? This would give you 6 minus 8i plus 9i, which is plus I, and then minus 12i squared, which of course we know is plus 12, because I squared is negative 1, so that gives you 18 plus I. So it's possible to multiply complex numbers and get a new one. That's kind of weird, because you couldn't do it with vectors, so this is kind of a different idea. And we also know you can divide complex numbers, right? And I'm not going to do this because it'd be a pain. Remember, you have to multiply by the conjugate, 3 plus 4i, 3 plus 4i. And then that'll make the i's go away on the bottom because conjugates always make the i's disappear. But it's a pain, right? And you have to break it up at the end. So the whole point of trig form is that it gives you a really easy way to multiply two complex numbers together. And it doesn't require foiling. It doesn't require complex conjugates. It's really, really slick. So what we're going to do here is we're going to kind of take this idea that z1 is, we'll call it r1 times cosine of theta 1 plus I sine of theta 1. And then we'll have z2 is r2 times cosine of theta 2 plus I sine of theta 2. And the question is, what is z1 times z2? And what is z1 divided by z2? And right now, looking at this, you could be thinking, oh man, we're going to have to do a lot of multiplication and foiling and stuff. I'm actually going to do a lot of that for you. And of course, that sounds a lot like something that requires a proof hat. So I'm going to write what I just wrote again. So z1 is r1 times cosine theta 1 I sine of theta 1. And z2 is going to be r2 cosine of theta 2 plus I sine theta 2. And we're looking for, we're just going to do the first one, the one we're actually going to prove is z1 times z2. Okay, so the question is, what do we get when we multiply those? So I'm going to do the work for you, and then you're going to see that we're going to come up just with a really nice formula here, so you're never going to have to work too hard for this. So let's do it. So z1 times z2. Well, if we multiply these together, I'll have r1 cosine theta 1 plus I sine theta 1 times r2 cosine theta 2 plus I sine theta 2. So this is our representation of our two complex numbers. Now we'll bring those r's to the front. So we got r1, r2. And now we're going to have to FOIL the rest of it. So cosine theta 1, cosine theta 2. And drop the parentheses here. And the outside terms would be plus I cosine theta 1 sine theta 2. Right, because we have I cosine theta 1 sine theta 2. I'm just trying to keep them organized, theta 1, theta 2. Inside terms would be plus I sine theta 1 cosine theta 2. And the last two we'll have, let's leave it as plus I squared sine theta 1 sine theta 2. And of course, I squared is negative 1, so we can change that next. So that's r1, r2 times cosine theta 1 cosine theta 2. I kind of group these in a special way. That's how a lot of proofs work, right? I squared is going to make a negative sine theta 1 sine theta 2. And then we have plus, I'm going to factor that I out, and I'm going to be left with sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. Now, some of you may be thinking, these look really familiar, right? What is this? Cosine, cosine, sine, 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 and this is sine, cosine, cosine, sine. Interesting. So we have r1, r2. This is cosine of theta 1 plus theta 2, and this is I sine of theta 1 plus theta 2. And this is our formula for z1 times z2. Now, I want to impress upon you what just happened. So we took multiplication of two complex numbers, which usually requires foiling, and what we said was, well, you just multiply the r's, right? So you multiply the r's together. That's in the front here. And then instead of having to do any multiplication in here, I actually add the angles. I don't multiply them, I add them. That's really useful because adding is a much simpler way to go than having to actually like FOIL or do anything like that with these complex numbers. That's really cool. So I am not going to prove the division one. If you want to try it, you can. It's very simple, works very similar. You have to multiply by a conjugate, but these are the very important 6.6 equations. We're going to use them today for your homework, and also we're going to use them in the next lesson for proving some really cool things called roots of unity. So if you have z1, I've written this before, but I'll do it again, is r1 cosine theta 1 plus I sine theta 1. And z2 is r2 times cosine of theta 2 plus I sine of theta 2. Then the formula we just came up with is z1 times z2 is going to be r1 r2 cosine theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. So you just add. And this is another cool one, z1 over z2. Well, in the front, we're going to have r1 over r2. What do you think we do with the thetas this time? Instead of addition, we subtract them. Theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So, two very important equations. Make sure you have these in your notes. We will be using them quite a bit in the next few days. So, let's take a look at an example. So, let's look at how easy this is. z1 is 25 root 2 cosine negative pi over 4 plus I sine negative pi over 4. So we can think about where that would be. Negative pi over 4 is down here at 45 degrees. And we got a distance of 25 root 2. I have no idea where that is, but let's say it's right there. Then we have 14 cosine of pi over 3. Pi over 3 is like up here. So 14 is going to be less than 25 root 2, something like that. The question is when we add or multiply these together, where does that end up putting us? So we're going to find the multiplication and put it into a plus bi form. To do that, we're going to multiply these two things. So z1, z2 is going to be 25 root 2 times 14 times cosine. We add these together. So it'll be negative pi over 4 plus pi over 3 plus I sine of negative pi over 4 plus pi over 3. Now let's actually see what this is. 14 times 25. If you have 14 quarters, how much money is that? Well, 12 quarters would be $3, so 14 quarters is $3.50. So this is 350 root 2 times cosine, let's see here, pi over 4 and pi over 3. That would require a common denominator of 12. Is that right? So this is 3 pi over 12. We have negative 3 pi over 12. And then plus 4 pi over 12. So that gives us 1 pi over 12. So we have cosine pi over 12. And then plus I sine pi over 12. So not great numbers, but they went in a plus bi form. So we're going to have to grab a calculator to finish this one off. Let me get mine. Let's see here. So we're going to do cosine of pi over 12. Cosine pi over 12. And then we're going to multiply that by, sorry, let's just leave that for now. So we have 350 root 2 times, I got cosine of pi over 12 is 0.9659. Plus I times sine of pi over 12. Sine of pi over 12. I get 0.2588. And now what we'll do is we'll distribute this number in here. So 350 root 2. And multiply that by our first number. And we get 478.108 plus 350 root 2 times 0.2588. And I get 128.108i. There we go. So we took our value, just multiplied the r's, added the thetas, found those in the calculator, excuse me, and then we were able to find our values. Not too bad. All right, let's try a different one. So this one, I'm thinking we might actually be able to do, well, we'll find out. I'm hoping we'll be able to do it without a calculator, because I kind of wanted to do one without one, but we'll see what happens. So this time we want to find the division. So z1 over z2, just use our equation. Divide these. We have 2 root 2 over 6 multiplied by, now we subtract. So it's going to be cosine of z1 minus z2, yep. So 135 minus 300. Plus I sine of 135 minus 300. So 2 root 2 over 6, that is root 2 over 3, times cosine of 135 minus 300, that's negative 1, what is it, 65? That is not a happy number. All right, well, we'll do it. And then we have plus I sine of negative 165. So, got to grab a calculator for this one too. So we do cosine, make sure I'm in degree mode here. So cosine of negative 165, and that's root 2 over 3 times negative 0.9659 plus I times sine of negative 165 gives me negative 0.2588. And if we distribute that root 2 over 3, root 2 over 3 gives me 0.471. Multiply that by our first number, negative 0.9659. I get negative 0.455 plus, do our root 2 over 3, multiply by negative 0.2588, and I get, so I should really do minus there. Get rid of that. So minus 0.122i. Yeah. So, nice easy way to multiply complex numbers. Sometimes they require you to change over to trigonometric form. Sometimes I want you to leave it. But much easier than dealing with complex conjugates and all that mess. Not an issue. All right. So here's one with no calculator there. I knew we'd find one. So if you want to give this a pause and try it on your own, I think that would be a great idea. So why don't you give that a shot real quick. All right, let's see how you did. So we have our first z1 and our z2. We're going to try the product and the division, both in standard form. That's a plus bi. So z1 times z2, we multiply 8 times 4 is 32. I'll write it out. 8 times 4. Then we times cosine. So pi over 4, that's 3 pi over 12. If you add one more pi over 12, we'll write it out. So we got 3 pi over 12 plus pi over 12 plus I sine of 3 pi over 12 plus pi over 12. And so that's going to give us 32 in the front, 8 times 4. And then we have cosine of 4 pi over 12, which is pi over 3, plus I sine of pi over 3. Hey, those are values we know. Cosine of pi over 3, that is 1/2. Sine of pi over 3 is root 3 over 2. So this gives me 16 plus, let's see, 32 times root 3 over 2, that is 16 root 3 I. There we go. The division, z1 over z2, it's going to be 8 over 4. That's a nice number. Times this time we subtract. So 3 pi over 12 minus pi over 12, that's 2 pi over 12. Just write it out that way. So I got that by doing 3 pi over 12 minus pi over 12. And then plus I sine of 2 pi over 12. Well, 2 pi over 12, of course, is pi over 6. So let's say we can do this in one step here. So 8 divided by 4 is 2. So this is cosine of pi over 6, which is root 3 over 2. Plus I times sine of pi over 6 is 1/2. Little unit circle there. The 2 is going to cancel from both, so we have root 3 plus I. Cool. All right, so a little bit of food for thought here, just to think about what we're going to be going to next. So if you have r cosine theta plus I sine theta, think about how you would represent z squared or z cubed or any higher power. And this is especially interesting when r is equal to 1. So this is just something to think about. Think about how would you do that? What would this look like if you were in a square or multiply or cube it? And especially if r is equal to 1, what would happen there? So something to think about, and we'll get back to it when I'm back with you guys. So I believe that's all I have for you. I love you guys. That's why I'm here. Have an excellent day. I'll see you soon. Bye-bye.